Hello! Initially, this lesson was called Hardware Requirements. I intended to talk very briefly about the sort of graphics hardware that's required to run the Seismic Terrain Explorer. The Explorer is obviously a graphics-intensive application, more so than any other geophysical program you have, and in terms of its graphics intensity, it rivals many of the 3D games that you might be playing. After thinking about it for a bit though, I realized that I should talk more about what goes on behind the scenes, because with the Explorer and with perceptive seismic interpretation in general, we are walking into a new world, and in that world we have a completely different focus. The world that we, as seismic practitioners, have lived in for the past 50 years was data-centric. Our entire focus was on producing more and better data. This new world is all about getting more out of that data. It's about visualization and virtual and augmented reality. Given that there are no geophysical courses on the subject, it's probably a good idea to give you a brief introduction to how this new virtual reality is created. So I'll give you a brief lesson on the brand new geophysical subject of tessellation. And I'll begin with the movie that is credited with starting it all. Pixar's Toy Story. Toy Story was released in 1995 and had been in production for more than 5 years. To understand why it was considered a revolution, consider that Disney's The Lion King was released just the year before. The Lion King was completely animated by hand and employed over 400 animators. Toy Story, on the other hand, was the first feature-length film to be completely animated by computer. There are no hand-drawn elements in it anywhere. Here are some statistics. It was eventually rendered using a render farm of 117 Sun Microsystem computers, running 24 hours a day. It was rendered at a resolution of 1500 by 900 pixels and at 25 frames per second. Each frame took between 45 minutes and 3 hours to render, and the entire movie required over 800,000 machine hours to produce. There'd been nothing like it before. So why did it take so long and so much computer power to produce? Let me show you how the whole thing works, because regardless of the complexity of the scene, 3D graphics always reduces to the simplest geometrical element possible: triangles. What you're looking at now is simulated terrain produced in an NVIDIA demo program. In terms of seismic terrain, this is pretty simple, but it will serve to make my point. Regardless of whether you're looking at Toy Story, or terrain, or a seismic image, or any of the multitude of 3D games that are available today, every object within it is built upon tessellation, which is the art of forming triangles. Here I have overlain the triangles that form the surface so that you can see how it's made. One of the things that's obvious is that the number of triangles in each area changes depending upon how far from the viewer you are. This is called adaptive tessellation, and everyone doing 3D graphics today uses it. We use it because the farther away from the viewer an area is, the less detail is needed to represent it. As you can see by this animation, as we zoom into the scene, the tessellation changes on the fly, and as the level of tessellation increases, so does the amount of detail that we can see in the scene. I use adaptive tessellation, very similar to this, in the Terrain Explorer. So this is how all 3D scenes are created, and getting back now to Toy Story, the reason it was such a success and such a revolution is that a typical scene, like the one you're looking at now, was built using 2 million triangles. That's why Toy Story took so long to render each frame. When you think about all the matrix calculations, lighting calculations, etc., that you need to put a single triangle onto the screen, you can understand why, in the era before massively multi-parallel GPUs came along, it took so long to produce a scene. And with that in mind, you might get some sense of why we were forced to use grayscale and variable density displays for so long. Speaking of that, let's now take a look at the Terrain Explorer and what it does.